When people hear AI, they tend to think about software, like models, chatbots, applications. But an AI factory is fundamentally different. It's infrastructure for producing intelligence at industrial scale. The easiest way to think about it is like a production line for intelligence.
The future is now, as they say, and it's very important for every stakeholder that is involved in the data center and the power generation side that they are conscious about the pace we're facing and all the challenges perhaps that they may need to overcome.
Every time you convert power, you're losing energy, and that lost energy gets released as heat. Power can be converted multiple times before it reaches the chip. But with AI scale, the inefficiencies become massive. So even like a 1% to 2% loss translates to megawatts of wasted energy.
Wood Mackenzie is tracking 220 gigawatts of new data center capacity currently sitting in the US pipeline. 183 of those gigawatts are already commercially committed. That's 22% of US peak demand in just a few years. We've spent a lot of time on this show and our sister podcast, The Energy Gang, discussing this precise topic. Today, we're going one level deeper. Not the megawatts, not whether the grid can cope. We're going to hear what's going on inside the building, on the AI factory itself. How does power flow from the substation all the way to the chip? And why is it being reimagined right now? I'm Sylvia Leyva Martinez, and this is Interchange Recharged, Wood Mackenzie's podcast where we explore how finance, policy, and innovation intersect to reshape the global energy transition. I'm back with you after a few months on maternity leave, and I wanted to thank Bridget Van Dorsten for carrying this show beautifully while I was away. But I'm really happy to be back on the show. My guest today is Nick Wright. Nick is a vertical marketing specialist of electrical products at Siemens. His sweet spot, in his own words, is the path that power takes from the grid all the way to the rack and the GPU, which is exactly what this episode is about. Nick, welcome to Interchange Recharged. I'm so happy that you're here.
Yeah, thanks for having me.
So let's get started and let's just take a step back because I think a lot of people within the audience, they have heard about the term AI factory, but what does that really is? Like just to make it a bit more concrete for all the power folks out there.
So just to level set, when people hear AI, they tend to think about software, like models, chatbots, applications. But an AI factory is fundamentally different. It's infrastructure for producing intelligence at industrial scale. So every prompt, every model, every inference is powered by electricity. So when we're talking about scaling AI, we're really talking about scaling energy. The easiest way to think about it is like a production line for intelligence. So a traditional data center is more of a cost center, if you would, while an AI factory is a value engine optimized throughout the output and input through the energy. So at scale, this stops being IT. It becomes more of an industrial infrastructure. So, AI factories, they don't just produce intelligence, but they reshape how we design energy systems.
So they're literally a factory. So it seems that the term is quite right.
Yeah, multiple racks, GPUs interacting for training and modeling. And really, it goes beyond what a traditional data center used to be. And it's multiple data centers kind of in a way talking to train these models.
I'm glad that you mentioned rack because I've been hearing like rack power, rack density, megawatt racks. So for someone who has never been exposed or has never been inside to a data center, what exactly is a rack and why is it so important in this conversation?
So a rack, essentially, it's the physical unit where the compute lives. It houses the servers and GPUs that are doing the work. Historically, racks maybe were 20 to 30 kilowatts, but in AI factories, that's changing dramatically. So today we're seeing racks pushing into the megawatt range, over 1 megawatt per rack, and that reshapes how we design everything around it. Imagine 1 megawatt density, the rack becomes the focal point for the power delivery, the cooling, the efficiency. I mean, we're no longer building a building and filling it with the IT. We're creating the entire facility around supporting these ultra dense compute units or what we're talking about as racks. As Siemens, we recently partnered closely with like NVIDIA, Invent to help create like reference designs to meet the needs of these latest 1 megawatt racks, like a Vera Rubin processor you may hear about. So the industry has shifted to truly powering the rack itself.
Okay, so it seems that the the foundation of the architecture is not the container or the building itself, is not your building around the computers, and all the engineering has to be thought precisely around that.
Absolutely. Yeah. To a precise, you get swings with these racks and GPUs. So it's about consistency and bringing power delivery that can really, as the models train, they can be consistent. And so is the power, good quality power.
So just to make sure, what is a GPU?
Yeah, so the GPU itself is a graphic processing unit. It's interesting because companies like NVIDIA that started really working with GPUs really was in the gaming system. Years ago, that's what NVIDIA was known for. But then over time, really using those graphic processing units for training the models is where AI kind of fundamentally changed.
Okay, perfect. So take us through that journey of the electron. You have already mentioned the big elements of an AI factory architecture. So if we go from the grid all the way to the inside of the factory, what does that journey look like, and where does Siemens come into play?
The power journey starts at the grid. It flows through substations into distribution units and ultimately reaches the rack where the GPU lives, that graphic processing unit. Traditionally, the journey involves multiple conversion steps. So it'd be AC power to DC power, DC back to AC, and then DC again. So every one of those steps introduces energy loss. So more heat, more complexity. That inefficiency becomes magnified at AI scale. So imagine that. Siemens sits across that entire value chain from grid to chip. We connect electrification, automation, digitalization into one integrated system. So that does include the substations, the switching, distribution, and even the digital twins that simulate and optimize performance before anything is built. The key differentiator is taking a systems level approach where power delivery, thermal performance, and operations are optimized together, not as separate decisions.
You mentioned that this has changed because of the sheer size of the racks has increased as well. So we're talking now about megawatt volumes or megawatt sizes for these racks, and also all the steps for the energy conversion imply losses. So could you please tell me what has changed over the past couple of years, thinking about the AC architecture now that systems are bigger and more powerful? Does that architecture still work?
Yeah, what's really changed is the scale and the nature of that demand. So AI workloads are dynamic. Like we mentioned earlier, they're incredibly power dense compared to traditional IT loads. At the same time, demand has become exponential and continuous, driven by these billions of AI interactions. So imagine traditional AC architectures were designed for predictable, steady workloads, not this kind of high density, high dynamic, right, demand. So what used to be reliable AC systems is strained. Simply just wasn't designed for megawatt scale racks and gigawatt scale campuses.
When we think about the dynamic component, I remember talking to Bridget on our last episode that we're seeing these peaks in power. So sometimes the processing unit is not being used as much, but those changes can be hundreds of megawatts in just a few minutes. So I would think that's where the challenge is coming from, that systems now need to be more sophisticated to be able to manage those rapid switches in voltage, among other things, of course.
Yeah, absolutely. I think the conversion is really is where the heat problem becomes an issue. So, every time you convert power, you're losing energy, and that lost energy gets released as heat. In the traditional architectures we spoke about, power can be converted multiple times before it reaches the chip. But with AI scale, the inefficiencies become massive. So even like a 1% to 2% loss translates to megawatts of wasted energy. The heat is a cascading problem. So more cooling is required, which consumes more power, which generates more heat. It really compounds as a cycle.
So at what point was there like this need to rethink about what the appropriately sized factory or solution looks like? At what point does this densification curve of the racks stops being more of a tweak and needs more of a foundational solution that is needed to avoid losses, as you were mentioning, and overall increase the efficiency of the entire AI factory?
It's something we've faced the last couple of years, but really we're crossing that threshold every day. It takes invention to really make sure we're keeping up with these changes. When you think about it, moving from kilowatt racks to megawatt racks, you're no longer making incremental improvements. You're fundamentally rethinking the architecture. At that level, power, delivery, cooling, compute are tightly coupled systems now that have to be designed together. So the conversation shifts from optimizing what we have, but really reinventing it.
Okay.
It's where seeing new architectures emerge. We're on the forefront with involvement with NVIDIA. Even in their Omniverse, we marry that to our digital twin composer. So we're creating and testing AI factories before they're even built, right? Digitally is a way that we can reinvent because we haven't actually been in the field putting something together and then testing. So that's been a huge win for us is kind of being able to take a digital twin from the beginning.
So it's good to see like how these new architectures can be tested, as you mentioned. You don't need to build an entire factory, which I don't think would be the most cost competitive
Right.
way to test things. So just in general, we already talked a bit about why the current AC or traditional AC architecture hasn't worked. So could you tell me more about what does this new DC architecture look like in an actual AI factory? And what is the main difference between these new DC architecture versus the traditional one? What is kept and what now disappears?
Yeah, to paint the picture, in DC architecture, the goal is to simplify the power path significantly. So you convert once and deliver DC directly to the rack. What disappears is all the unnecessary conversion infrastructure. What replaces it is the more direct, efficient path to compute. So, kind of in a way of phrasing it, it's not that AC is going away completely. It's still the backbone, but DC becomes the efficiency layer that brings the power closer to the chip, both physically and in the architecture.
So, what role is Siemens playing in all of this? Like, is it on specific parts of the or specific components? Is the design itself? How is it?
Siemens is heavily involved as an end-to-end solution. So visualization through digital twins, all the way down to medium voltage, transferring down to low voltage, and then also just the monitoring itself. We have certain ways of like our smart gear solution that shows the amount of uptime, the efficiency, and also the monitoring and maintenance of the actual low voltage solutions that you have in the actual data centers. So I think that's another key component that we're looking at is from an end-to-end level. What can we offer throughout the entire data center and AI factory power distribution?
You have been mentioning throughout this conversation that we're gaining efficiency and we're reducing losses because of heat as we're reducing the steps from AC to DC conversion. But what type of efficiency gains are we really talking about? Is it 1%? Is it 0.5%? And why is this increase relevant for the AI conversation?
Yeah, so at first glance, the gains of 1 to 2% might sound small, but AI factory scale, they're enormous. A single percentage of efficiency can translate to millions of dollars in savings and significant increase of the tokens themselves. So beyond conversion efficiency, you also reduce cooling demand, lower copper by up to 45%. Basically you're shrinking the infrastructure footprint. So the real gain isn't just efficiency, it's overall system performance measured in something new, which is tokens per watt. These type of energy efficiency solutions, they can save data centers more than 2 million kilowatt hours. And we did something similar with Nova data centers back in 2024.
So this is not necessarily a new solution. It's a different way of using existing technology and also existing engineering. So changing how AC and DC are currently interacting and ultimately gaining all these new efficiencies that you were just talking about.
Absolutely. And just partnerships in general. What is being built for the future? How do we actually meet the demands now, but be scalable 3 to 5 years, 10 years out because it's rapidly changing in the market?
Right now, we're talking that the current power that is used in these factories is 800 volts DC. So when we think about the outlets in our houses is 120 volts. So I would assume that everything related, protection schemes, breakers, and even the people that are working there needs to be some sort of protection or added protection compared to traditional AC architectures and in general working with lower voltages. So could you tell me more about this?
You're right. The 800 volt DC is becoming critical. It allows you to handle extreme power density and more efficiency. The higher voltage means lower current, which reduces the heat, enables smaller cabling, and improves the overall system performance. It does, like you said, it introduces new considerations for safety and protection. That's why solid state breakers, the fastest fault detection, has become important. The benefit is resilience. Faults can be detected up to 100 times faster, protecting extremely high value compute systems. And Siemens is developing and creating right now, alongside this 800 volt DC breaker need to enable that safety and the efficiency. The solid state breaker will detect interrupting faults into microseconds. So the resilient, safe, efficient, and scalable power is what we're focused on.
When thinking about those very high voltages, you cannot leave safety aside. So I'm glad that we're seeing all these new types of solutions. And I'm sure that as computers become more sophisticated, these AI factories continue growing, all the safety features are going to be growing along as well.
Yeah.
But we've been talking a lot about the building, the racks, the power needs inside the building. Let's take it out of the building. So what does this mean for the utilities, the ISOs, like all the stakeholders that are thinking about how a new data center is going to affect the grid dynamics? If we make the power distribution more efficient, as you were mentioning earlier, then what does this mean upstream? What does this mean for all these stakeholders that are focused on the grid side?
If AI factories become more efficient, which is our focus, then they don't just need to, reduce demand and how they change and how demand behaves, but these facilities can become highly flexible energy consumers, so capable of shifting those workloads and participating in demand response. So I kind of see it as it creates an opportunity for AI factories to act as a grid balancing asset. This is what we mean by grid-aware infrastructure. Systems that are not just consuming energy, but actively interacting with the grid in more intelligent ways. So we're kind of evolving as a power system. Ideally, AI factories, they live and breathe energy with the grid. So hopefully the grid scale and the future-ready AI factories that interact with the grid, it really just becomes more flexible. I don't think of it as just something that's pulling from the grid, but it's also giving back.
That would be the ideal case. We've been discussing that in the episode. This is the large scale side, but we have also discussed the residential side, even on the EV front, that maybe your car can also be an ancillary services provider for the grid on a very small scale, distribution side. So it would be ideal that we could have more of this interaction instead of having just load centers and generation centers, just flexible assets overall. One thing that we've been discussing at Wood Mac is the sheer volume of new load that we're expecting over the next decade. We have tracked 183 gigawatts of large load that have already been commercially committed. So there is a high likelihood that this new load is going to come online over the next few years. Right. There are issues with substation, transformer lead times. We have also seen issues with labor competing on the generation side. In PJM, the utility commitments are already running 3 times higher than the accredited capacity in the generation queue. So the grid is already buckling. There are already issues there. So now we have not only the load side, but these new component of new equipment that we have been discussing. So Nick, do you think the industry is just trading one bottleneck for the other? Like even if we're increasing the efficiency, the volume is already there.
I see your point, and in some ways, I respect that, but really we're innovating, right? That's the goal. So the challenge is how we respond to those demands and constraints. So instead of just building more, we're focusing on our smarter infrastructure, microgrid, storage, and flexible demand to make those better uses of the existing resources. I can see an industry where we're collaborating, working closely with our partners to solve it. Ultimately, this will reshape how we distribute power for decades, right? We're just at that point where we have to innovate rather than just build more capacity.
We're also seeing new types of solutions on the power generation side and how they are interacting with large load. And that's something that I wanted to briefly touch on because we have these fully grid connected assets that they are going to be pulling power from the grid, but also we're seeing more of the behind the meter solutions, flexible power, transitional gas, so to say, while the data center can get connected to the grid. So all different kinds of solutions. So let's say if we compare a purely front of the meter connected load versus one that has behind the meter generation, Does that have any significant implications for the AC to DC architecture?
I mean, absolutely. Our shift is going towards microgrid enabled campuses, integrated storage, and co-location. So we do have to think, for the future for that. And AI factories are increasingly being designed as part of the energy ecosystem. So not just as those standalone loads. And Siemens is playing a key role here, connecting hyperscalers with utilities, enabling technologies like the grid enhancing solutions we mentioned. Plus, we partner with companies like Soluna. They basically help deploy behind the meter power and controls approach to the managed grid. So GPU swings and the running AI and high performance workloads will be more direct and be used more in a renewable state.
So I would like to spend a bit of time talking about some of the bottlenecks that we're seeing. Like, we're already seeing them on the generation side, and I would think there is a similar issue on the data center side. So you were teasing supply chain a bit earlier in the episode. I said that Siemens has just crossed $1 billion in US manufacturing across different states in the US. Why is this investment happening now? Is that a way to address some of the bottlenecks that we've mentioned before? And how much of these bottlenecks are being driven by the items we just discussed about volume, about the challenges with having a new architecture, general adoption of these new technologies?
The investment's really about timing. So AI, electrification, industrial growth are all set and accelerating at once. So driving unprecedented demand for the power infrastructure. Our scaling and manufacturing capacity, we've been in California, Texas, and Carolinas growing. It's really to meet the needs of the AC demands today, but while investing in those next generation DC architectures. So medium in voltage and low voltage is needed now as we scale for the future. Plus, it's great for like made in American factories and labor, which NEMA focuses on with their new designation. So we're seeing supporting current demands and prepping for an industry that's going to change for 5 to 10 years ahead of us. So manufacturing capacity is very important from a production side.
Definitely. And we have seen these on the renewable side. All the new module, wafer, cell capacity has increased over the past few years. And it's precisely to address some of those bottlenecks and the importance of developing a domestic manufacturing industry. So I'm glad to see that this is not only happening on the renewable generation side, but also it's expanding to the load itself and the components that are needed to bring all these new data center capacity online with US made materials.
Exactly.
One of the other bottlenecks that we have been seeing on the renewable side, and this has been an issue for a while, is skilled workforce. There are not enough workers. There are not enough electricians. So how is Siemens facing that problem? Like, ultimately, you're competing against other infrastructure projects to secure that people. So how are you facing these bottleneck?
Ultimately, you can't scale infrastructure without scaling the skilled workforce to build and operate it. These initiatives that we have to, equip students and career changers with technical and digital and safety skills, they're for the jobs of today and the future. Siemens, we have a separate group, our foundation, that actually started an initiative called Careers Electric recently. And Siemens has invested heavily in workforce development. We even have Siemens Educates America, which is a group that I work with. And some don't realize, not just any electrician can work on a data center job. This is a niche part of the industry where specialized training is needed. Most of the work to do the jobs safely and things in an environment that is safe to be protected before you even get on the job site. So, we're passionate about creating content and meeting the needs of those new learners, the millennials and Gen Zs that are looking for jobs, and in kind of inspiring to choose the trades. So we do have learning labs and virtual experiences with Siemens Educates America and our NUMA platform that explores this at the trade schools.
I love this. I love this corporate social responsibility component. I love that it is effectively addressing a bottleneck that we're seeing in the industry. So it seems that it's a win-win situation for everyone. So kudos to Siemens and the Siemens Foundation.
Absolutely.
So just to wrap up on the bottleneck front, we already talked about some of the issues that we're seeing. We talked about on what Siemens is doing. Let's talk about what our audience should be thinking about when trying to address these bottlenecks. So if we think that we have developers, we have financiers, we have the IPPs, they are facing these bottlenecks too. So how they should be thinking about them and what they should be addressing right now when they're planning for their projects.
Yes, so they need to treat power differently. The infrastructure and the strategic constraint, that needs to be a thought from day one, not something that we solve later in that process. That means integrating energy and efficiency and deploying timelines early into planning. It also means investing in that workforce readiness because speed to deployment is becoming a major competitive advantage. Data centers that are getting upspin and put together, that they have a plan to have it within a year or two. If it goes to 3 years or 4 years, we're already changed what the model is. So it needs to be a quick response to those demands.
Let's jump to the final stretch of our discussion. And one thing that I'd like to cover is, you mentioned in our prep call that we are at the very beginning of a big transition. So from where you're at Siemens, you're talking to developers every day. What are the 2 or 3 biggest misconceptions that they have when they come to you asking about DC architecture and all these new solutions?
I think the biggest misconception is that DC replaces AC, and it really doesn't. It complements it. So AC remains the backbone, while DC enhances the efficiency and all the way to the rack level. Another misconception is that this is far in the future. When elements of DC architecture are already being deployed today, because the economics just demand it.
I like how you're framing it because, yes, we're just at the beginning of this transition, but the action that we're seeing across the energy front, the AI front, is just growing exponentially. I feel that there is a new model every month. The power capacity is just scaling at a pace that I had not seen personally before. And we have covered in previous episodes that this is being reflected in the number of utility commitments, in the number of new data center announcements that are quite serious and that are highly likely to materialize. So the future is now, as they say, and it's very important for every stakeholder that is involved in the data center and the power generation side that they are conscious about the pace we're facing and all the challenges perhaps that they may need to overcome, some of which we've already been discussing throughout the episode. So thinking specifically about the energy stakeholders, who is most at risk of getting it wrong? So practically, what does it look like? Is it a stranded asset? Is it a campus that can scale? Maybe even like a fire? What does it look like? What getting it wrong actually looks like?
Yeah, that's really works on a lot of different levels, but because it is a lot of partnerships and collaboration to meet these demands, I think the biggest risk is for the organizations to think it's incremental change rather than a systems level shift. So really, like we discussed earlier, everything in regards to generating the power and building the building around that rack is so important because, getting it wrong, it looks like underestimating power constraints and then overbuilding the inefficient infrastructure and failing to integrate energy strategy early. I think the winners will be the ones who holistically work together across power, compute, and the operations piece to really meet the energy efficiencies now, but also scale for the future.
I love this because this is a conversation that we've had as well on the renewables front, where before it was more of a siloed work. So it would be the procurement side just working on getting the modules, let's say. And then the engineering side would be working earlier in the process. There was not a lot of communication. Now it has to be cooperative. As you mentioned, it has to be a holistic approach because everyone needs to work together now to make sure that the project that they are designing right now is going to be economically feasible when it actually gets built in the next 3 to 5 years. So it seems that same cooperation is needed on the data center development side, and I'm glad to see that these conversations are already happening. So let's see how that partnership evolves over the next few years.
Right.
So from all the conversations that we've had, what are you hearing in terms of what the architecture needs to be over the next 3, 4, 5 years? And what does this tell to the rest of the energy industry?
Yeah, so our customers, they're really designing power, density, and efficiency, pushing architectures that integrate computing. I think cooling is a big topic, and powering everything as one
Mhm.
system. Their focus is really on tokens per watt and that end-to-end performance. And it's signaling the industry that infrastructure must evolve quickly, just as much as Silicon Valley is. We have to do it from a power distribution side. So it reinforces the idea that power is the new central innovation around them. I think of it just like we transformed for our forefathers. We experienced when the railroads were being built back in the 1800s. The demand for AI in our world drives this now. And the compute race is very real and it's moving exponentially fast. So working with these customers and partners, we have to be innovative and make sure we look at a future-ready design.
And taking it back home, what should a developer or a financier be thinking right now if they're planning a facility right now?
This is the year to align on infrastructure strategy. Really, it is. Securing power
Okay.
access, investing in efficiencies, building the partnerships that we mentioned to build a full ecosystem. And I really appreciate you saying, it takes utilities, developers, and investors. They all need to think in terms of integrated systems rather than siloed decisions. And critically, they need to invest in workforce development, avoid those future bottlenecks, maybe try to inspire current next generation to see the opportunity in the job market so we get more with the skilled trades, and also just really investing that power is going to be an essential force to make sure these AI factories and data centers work properly.
So, Nick, before I let you go, if you had the audience leave with one thing from this episode, um, what is the single thing that the industry is underestimating now about the AC to DC transition?
I think really the most underestimated aspect is how central efficiency is competitiveness, right? AI scale, every conversion loss translates to directly to the compute and the loss value that we see. The shift isn't just DC as the technical upgrade, but it's about removing inefficiencies from the systems that we have today, and ultimately refining that energy and compute working in unison together. That's the goal.
Amazing. Nick, thank you so much for joining me today. This has been a great conversation.
Yeah, thanks for having me, and I'm looking forward to future conversations and where the future goes. So I really appreciate it.
Nick Wright, Vertical Marketing Specialist for Electrical Products at Siemens. Nick, thank you for your time. And thank you, Siemens and Siemens Foundation, for all the work that they're doing on the workforce side, because none of these can be achieved without the power of the people. And to our audience, thank you so much for tuning in. We will continue talking about the grid to load interface throughout the rest of the year, among very other exciting topics on the clean energy space. If you haven't already, subscribe to Interchange Recharged wherever you get your podcasts and on YouTube. And you can find more of Wood Mack's research on data centers at woodmac.com. I'm Sylvia Leyva Martinez, Research Director at Wood Mackenzie, and this was Interchange Recharged. Thank you so much, and I'll see you in 2 weeks. Gracias.